So in this video, we're going to be going over how to solve an equation with an inductor using differential methods. Um, so this is what the circuit originally looks like. At time equal to 0, the switch is going to open. So before the switch is opened, the switch has been closed for a very long time, which means that our inductor will have this voltage supply running through it for a very long time. And whenever inductors have a voltage circulating through them for an infinite amount of time, they actually can act as a short. So I'm going to redraw the circuit with the inductor as a short. So I've redrawn the circuit with the inductor replaced by a short. And now what we're looking for is we're going to look for the current through the inductor. As you can see, this resistor right here gets shorted. So now we can find the current by just calculating the current inside this loop right here. And that's going to be equal to I.O. So we're going to use Ohm's law, V equal to IR. But we're looking for current, so we're going to actually have I is equal to V divided by R, and that's just done by rearranging that equation. So the I.O., or the initial I before the switch is opened, is going to be equal to our V, which is 12, divided by our resistance, which is just 6 because the other one got shorted. So we're going to be left with 2 amps. Next, we're going to look at the circuit after the switch has been opened. So I've redrawn the switch open for the circuit, and as you can see, this whole voltage source right here gets shorted out because there's an open circuit right here. So this can actually be redrawn as just that resistor right here, the inductor, and then the other resistor right here. This top resistor plays no part in it. Since it's not really attached to anything, it doesn't really do anything, so you can kind of cancel that one out too. So we just have the 2 Henry inductor there, and then we have this 6 ohm resistor here. So the differential method wants us to get it in the form of A1 dy over dt plus AO y is equal to F. So what we're going to do is we're going to take this circuit right here that we just found, and we're going to do a loop on it, a KVL loop. And we're going to say that there is some voltage for the inductor. So there's V inductor, which we're going to say VL, and then there's going to be some voltage for the resistor. So we can call that VR. Okay, and the way that I've drawn my current, it's going to go into the positives and out of the negatives. So this one's going to go into the positive right here when it loops back around, and out of the negative. So that's how we're going to label that. So when we go around that loop for KVL, we're going to get a voltage of VR plus a VL is equal to 0. Now we just have to solve what VR and VL are going to be. We know from Ohm's law that V equal to IR. So the voltage right here is going to be the R, the resistance, times that current. And the R right here is just supposed to be like a little subscript R. It's not supposed to be that big. For the VL, it's going to be a little bit more complicated. We have to pull out our differential equation for inductors, where we know that for inductors we have V is equal to L di dt. So we can go ahead and replace this in the formula here. So we have plus L di dt. And that's going to be equal to 0. So now that we actually have it in the form of A1 dy dt plus AOY equal to F. Um, Here our AO is going to be R. Our A1 is going to be L. And our F is going to be this 0 right here. So I have them switched a little bit. So now a really easy way to remember this is that we can rewrite it as A1 over AO dy dt plus y is equal to F over AO. Where in this case, the A1 over AO is going to be equal to our tau, and our F over AO is going to be equal to our K1. And I'll show you how that plays in just a second. So our general equation for these circuits with inductors or capacitors is going to be x of t is equal to K1 plus K2 e to the negative t minus t initial over tau. So now we're just going to flip back to the other page and we're going to find our K1 that we have and our tau, and then we are going to solve for K2. So here for our AO we have the value of R, and for our A1 we have the value of L. And then we have tau is equal to A1 divided by AO, and then our F was equal to 0. And our K1 is going to be equal to our F divided by our AO. So if we just sub these in here, the value of our resistance was, for this one right here, we only have that one resistor, which was 6 ohms. The value of our inductor was 2 henries. And we want to make sure that we're using the values from after the switch has been switched. So if we just replace those in, then we have 2 henries. Oops, that was supposed to be a 6 right there. 2 henries divided by 6 ohms, which is going to give us 1/3 for tau. And then our K is going to be equal to 0 divided by the 6 ohms, so we're going to get 0 for that. Now, we know that initially we had our I.O. was equal to 2, and that was at time is equal to 0, because it was before our switch was opened, sorry. At time equal to 0, our I initial was 2 amps. So we can say that x0 here was equal to 2 amps, and that's when we're going to replace our t right here with 0, because that's the time, and then our very, very, very initial time was also 0, because we started it at 0 as well. So we have K1, which is 0, plus K2 e to the 0 minus 0 over tau. So in this part, tau doesn't really matter because it goes to 0. So we're going to have 2 amps is equal to K to the E0, which turns into a 1. So K2 is equal to 2 amps. So now we can just go ahead and place that back up into the equation. So we have xt is equal to our K1, which was 0, plus 2 amps times e to the negative t, and in this case, since we just have a t here and we haven't replaced it with any time, we're going to leave the t as t up here as well. Our t initial, our very first t was 0, so we can leave that out, divided by tau, which is 1/3.